And welcome to High School Physics Explained. And today I would like to go through the answers to the 2017 HSC Physics paper. So let's get started. So the first question is, who was the main advocate for the distribution of DC to cities? Well, the important key term here is DC. And in the Battle of the Currents, we had the competition between Westinghouse, with the technical support of Tesla in terms of AC, against Edison for DC. So the answer is A. Question number 2. Which of the following is an inertial frame of reference? Well, an inertial frame of reference means that the acceleration is not present. It's 0. So if you look at all the responses here, a rocket launch, a car turning a corner at constant speed, a lift slowing down as it approaches, these are all accelerated situations. So B, being traveling at constant velocity, is our only possible answer for an inertial frame of reference. Question 3. Which of the following correctly shows the electric field between two parallel charged plates? The whole principle here is to understand electric fields always show you the line of force that a positive test charge will experience. And so therefore a positive test charge placed anywhere in this field right here will accelerate towards the negative plate. So that is the only answer. A. Question number 4. An astronaut with a mass of 75 kilograms lands on planet X where her weight is 630 newtons. What is the acceleration due to gravity on planet X? Well, this is a simple understanding. Of course, that weight is equal to your mass multiplied by the acceleration due to gravity. And so since we're working out the acceleration due to gravity, that G is equal to the weight divided by the mass. Now, our weight in this case is a force, of course, of 630 newtons. The mass is 75 kilograms. And so if you calculate that out, you get 8.4 meters per second squared. And so therefore, B is our answer. 5. An electric current flows in undoped silicon. So we have an intrinsic semiconductor. And so we have basically a band structure where you have electrons in the conduction band, and the holes are created from those electrons moving from the valency band. So therefore you have two flows going on. The electrons are of course attracted towards the positive plate of the potential difference applied, and the holes go in the opposite direction, but they're in the valency band. But the important thing is undoped, the number of holes is equal to the number of electrons, and so therefore the only possible answer is D, equal numbers of holes and electrons, but they're moving in opposite directions. Question number 6. Which of the following best represents the structure of a metallic lattice? A lattice means they are geometrically arranged. So we're looking for positive anions or positive nuclei, so to speak, arranged geometrically, and the electrons, of course, are flowing in terms of a sea of electrons through that. The only possible solution there is B. Which of the following is a statement about the Michelson-Morley experiment? Michelson-Morley's experiment, of course, was an experiment to verify the existence of ether by measuring the speed of light traveling in opposing directions, or at least right angle directions, of the supposed ether. Now, it was a valid experiment and a very reliable experiment. It's just that they got a null result. And so out of these statements, which is correct? It certainly did not prove the existence of luminiferous ether. In fact, they never actually were able to detect it. It did compare speeds of light, but the light that they compared were along perpendicular paths, so B is incorrect. It was invalid? Well, I just made its point. It was actually a valid experiment, so that is incorrect. Ultimately, it was unable to detect the motion of Earth through the luminous ether, so that is our possible answer. The answer is D. Question number 8. An electron is fired in a vacuum towards the screen with no electric field being applied, and the electron hits the screen at point P. A uniform electric field is turned on, and another electron is fired, and it strikes at the point Q. So we're clearly getting a field that causes the electron to be experiencing a force in that direction. With the electric field still turned on, a proton is fired towards the screen from the same starting point as the electrons with the same velocity. At what point does the proton strike the screen? So this is a little bit more difficult than previous questions. The first thing you should understand, of course, is that the proton is positive. So therefore, if an electric field causes an electron to move in that direction, my proton will experience a force in that direction. That automatically excludes A and B. But the real important thing to understand is that although they experience the same charge, their force, of course, that they experience is equal to the electric field multiplied by the charge. It's the same charge. So they're both experiencing the same force. But the mass of a proton is significantly greater than the mass of an electron. So therefore the acceleration of the proton will be significantly smaller than the acceleration of the electron, simply due to the fact that the acceleration, due to second law, is inversely proportional to the mass. And so therefore you will find that the particle will strike not at the same distance away, but a much closer distance away. And so for the answer is C right there. 9. What does the multi-cross apparatus demonstrate about a cathode ray? Well, they travel in straight lines. Yes, a cathode ray is a beam of electrons, but the multi-cross doesn't verify that. We don't know whether the electrons are absorbed on the metal surface or are rebounded off the metal surface, so it doesn't provide information about that. And we certainly know that the electrons are affected by magnetic fields. Multi-cross doesn't actually show us that, so the answer is A. Question 10 is a little bit more challenging. So here we have a rotor here, and we clearly see here a split ring commutator. So it's a generator connected to a galvanometer. And so this loop is rotated continuously in a clockwise direction as viewed from end nearest to the galvanometer. Which of the following correctly identifies the type of generator and the movement of the needle of the galvanometer? Well, first of all, the fact that it is split ring commutator tells you straight away it's a DC generator. So automatically we have excluded B and D. And so if you struggle with this whole concept, now you at least have a 50-50 chance of getting it correct. The question, of course, is which ways does it swing? Well, the galvanometer automatically swings only one direction. So it cannot swing between the positive and the negative. So that is incorrect. So it's going to swing this way. And of course it does swing in the positive direction because of the current going in this direction. Therefore, you could say that this, if this was a terminal, this would be the red terminal over here, and this would be the negative terminal over here. You know that when you connect up a galvanometer, you always connect red to red, so the galvanometer is actually correctly wired up, and so therefore you would expect the needle to head in the positive direction. And again, that confirms to us that the answer is A. Question 11. An AC source is connected to a transformer having a primary winding of 900 turns and connected to the secondary winding of 450 turns. And then we've got is a pair of parallel plates at this point there. And of course, here's the AC input. And so we know we have a 340 volt input. The question, of course, is what is the voltage at this point here? Well, the voltage here is going to be a lower voltage because if you can look at the number of turns, it is a step down transformer. And since it's half, we automatically know that the voltage here will be 170 volts. You now have to calculate the maximum field strength, in other words, the electric field, in this case between these two plates. And so as a result, you work out the electric field is equal to the voltage divided by the distance between the plates. And so you have 170 divided by the distance, which is 0.01 meters, and as a result you get 1.7 by 10 to the power of 4, which is C. Question 12. A satellite orbits the Earth with an elliptical orbit that passes through position X and Y. Which row of the table correctly identifies the position at which the satellite has the greater kinetic energy and the position it has the greater potential energy? To work that out, you need to understand that as we move away from the Earth in that direction, our potential energy will increase in that direction. And of course, eventually it becomes zero. So all of these values up here are negative, but we have an increasing potential energy. But you don't get energy for nothing. So as you move away, potential energy increasing, but if it is in orbit, kinetic energy must decrease by way of the law of conservation of energy. And so therefore at Y the potential energy must be greater than X because X is closer. But of course the kinetic energy must be greater at X than at y, simply because it has less potential energy. So if you look at the responses that we have here, the greater kinetic energy is at x. The greater potential energy is at y. And so therefore our only answer can be B. Now a little bit more complex question. You may not have seen a question like this before, but it isn't particularly difficult once you understand what's going on. So we have three sides of a triangle or three parts of a wire in a magnetic field. A force that is exerted on a wire in a magnetic field is only if part of that wire is perpendicular, or the current is perpendicular to the magnetic field. And so as a result, what you should automatically see is that these wires will experience different forces. First thing is that this part of the wire is not going to experience any force because it is parallel to the magnetic field. In this section, it is this component of this section that it will experience a force. In this side, it will be this component that will experience the force. And so therefore, if you use your right-hand rule, the current, if its current is going to go that way, it will experience a force, in this case, into the page on this side. This side, it will experience a force out of the page. So the question says, which way will it rotate? Well, it's not going to rotate around the YZ axis because there's no force pushing this here at all. So as a result, if this is going out and this is going in, you know it's going to rotate about the WX line. So therefore, these are possible answers. What's R going to do? Well, I've just established that's going to go in and P is going to go out. Since we're only looking at R and P, R is going to go into the page, and so therefore the answer is C. We're getting a little bit more difficult again. The diagram shows a DC circuit containing a transformer. It's a DC circuit. So the fact that we've got transformers, that's the first thing you should have noted. The potential differences of V1 and V2 are measured continuously for 4 seconds and the switch is initially closed, so there's a current flowing through this. At t equals 2, the switch is opened, and which pair of these graphs shows us the potential differences of V1 and V2, how they vary over the whole 4-second interval? Well, the first thing, of course, is that if we just concentrate on V, we note that we have a DC supply, so we have a constant voltage, and then it is switched off. So if you look at the possible for V1, constant voltage switched off, constant voltage switched off. These have no voltages, so therefore automatically C and D are excluded from our responses. The switch is switched open. Now, the thing is, if there is a constant DC supply here, we do not have a change of flux here, and no change of flux means no EMF generated on this side. So as long as the switch is on, this should be 0. When this is off, this is also 0, obviously. But momentarily, when this is in the process of switching off, you actually have the change of flux occurring here, which means you're going to get a little blip of a voltage over here. Because this is switched off, the blip will be in the opposite direction and therefore a positive flip. It certainly is not this response, and so our only answer is A. A car is traveling at constant speed following the path shown. An accelerometer that measures the acceleration along the XY direction is fixed in the car, which graph shows the measurements recorded by the accelerometer over the 20-second interval. The first thing you should understand is that the acceleration as it goes around the loop in a circle is always pointing towards the center. Now, of course, the direction will constantly be changing, but the magnitude of that acceleration is always equal to v squared over r, and since v is constant, or the magnitude of v is constant and r is constant, the acceleration will be a constant value. And so therefore, while it is in the loop, you should get a acceleration that is constant, but a non-zero value. However, it is about when it's entering. So as it entering here, it's making a sharp turn. In fact, the turn is much sharper than the curve of the radius. So therefore, the acceleration in this case is in the opposite direction, but a larger amount, but only for a small amount of time. This is true also when it exits the circle. So you're going to get a large acceleration in the opposite direction over here. With that in mind, you should get a strong, if we make inward positive, a strong negative value positive value as a result because the acceleration is going in. Therefore, B is our only possible answer. Question 16. 16 is a little bit more challenging. The AC supply is connected to a light bulb by two long parallel conductors as shown. Which graph shows the variation over time of the magnetic force between the two conductors? Is it all attraction or repulsion? Is this a sinusoidal wave or is it D? Well, the first thing to understand is that we have an AC supply, and so therefore when we have electrons, they are basically going backwards and forwards. This is true, of course, also of the current on the other side. But the assumption is that if the electrons here are going in that direction, then at that time, assuming that this length is of a specific value, and this is where it gets, the reality is the physics is a little bit more complex, we're going to assume that the direction, of course, is in that direction. So in other words, they're opposing, and that's repulsive. But of course, if the electrons are going in that direction, and on that side they're going in the opposite direction. So again, we have a repulsiveness. So you could argue, well, it's constantly repulsive. However, if you follow the motion of the electrons, they follow a sinusoidal curve. That means they go fast, they slow down, they stop and change direction and go back again. So the moment that they are changing directions, both sides, the electrons are stationary. And so therefore, at that point, there is no repulsion. And so you should get a repulsion force that is constantly there, but changing in magnitude. Therefore, our only possible answer is D. Question 17. A magnet rests on an electric balance. We've got a rigid copper rod runs horizontally through it at right angles to the magnetic field. The rod is anchored so it cannot move. And you can see at the moment with the switch open, really important that you look at diagrams closely, we get a value of 0.2 kilograms, which is actually responding due to the weight, but it's calibrated to measure, of course, the mass. And of course, it's measuring here simply the mass of the magnet. The question, of course, is what happens when you switch it on? When we switch it on, we're going to get a current that is going to go in that direction. So using your right-hand rule, you know that therefore the force that is exerted on the wire will be, since the magnetic field lines are going in that direction, is going to be in the upward direction. But the fact is that even though the force will be in the upward direction, the wire here, or this pole here, is fixed. So therefore, you're going to expect the magnet to therefore respond by being pulled down. So this value is going to increase. So now let's have a look at that. So therefore the reading afterwards will definitely be an increase. So therefore C and D are excluded. But this scale is designed to be calibrated for mass. And the mass, of course, is equal to the weight it's reading divided, of course, by the acceleration due to gravity. That will give you your mass. And so therefore the correct value will be the 0.2 plus the force due to the motor effect, but that force has to be divided by 9.8 to give you the equivalent in the mass. So B is our answer. Question 18. So let's look at this question. A particle of mass m and q are traveling, enters a velocity v and enters a magnetic field of magnitude b and follows the path shown. So a second particle enters a magnetic field of 2b magnitude with a velocity of half v and follows the identical path. What is the mass and charge of the second particle? Now the way to work this out is simply to say mv squared over r is equal to qvb. Now if you look carefully, you can see that we have circular motion here. That's what this is all about. And the circular motion, the centripetal force, is due to the force due to the charge. Of course, the v's cancel, and so we end up getting mv over r is equal to qb. The trick with this question, however, is to understand they follow an identical path. So therefore the radius in both situations is constant. So I'm going to create a formula where the radius is my subject, and so I get mv over qb. So that gives me that set radius. The trick now is that if I substitute in these combinations, will I get mv over qb? And if you look carefully at the relationships, the only possible answer will be C. And I'll verify that. So if I do C as a possible solution, I have m, and that is equal to 4m. I have v, which is equal to half v. I have q, which you're told is still q. And I have 2b, and I have 2b over here. Now, if I put the numbers to the side, you'll notice that I get 4mv over 4qb. Now, the 4's cancel out. This still leaves me with my ratio of mv over qb, which of course was equal to r, so therefore C is my only possible answer there. 19. Last two questions, which are a little bit more difficult. The Earth's magnetic field is shown, and the students standing a few meters apart at the equator at point X and Y, so there's X and Y, where Earth's magnetic field is parallel to the ground, hold a loop of copper wire and they spin it. And part of the loop is rotated like a skipping rope while the other part remains motionless. So this is the area we are interested in. So at what point at A, B, C or D do you have the maximum current from P to Q? Well, the first thing to understand is that we have magnetic field lines that are going into the page relative to this couple here. Now, for generation to occur, the motion of the wire must cross the magnetic field lines. That's giving you change of flux. Since B is moving with the direction of the magnetic field here, and D, the skipping rope, is moving towards you in completely 180 degrees to the magnetic field, both of those are not going to produce an EMF and therefore no current. So B and D are excluded. However, it's important to understand we want a current to go from P to Q. Now, whether you use your left hand or your right hand, you need to look at what the direction of the current is with the induction in place. And if you use the correct rule, then you will find the best value is C. So if C is moving down and the magnetic field lines are going into the page, that will cause a current to go from P to Q. So C is our only possible answer. Finally, the length of the spaceship is measured by an observer to be 3.57 meters as the spaceship passes with a velocity of 0.7 c. At what velocity would the spaceship be moving relative to the observer if its measured length was 2.5 meters? This is question 20 here, so it's not a quick pick of the numbers here to substitute to see which matches up here. You have to do a couple of calculations. And the first thing to understand that the value here is the length contraction as observed by a stationary observer. So we know this is going to be LV. In other words, it's going to be the contracted length, and we need to work out the actual proper length. Once we work out the proper length, we're in a position to work out the speed so that its new length, contracted length, will be 2.5. So let's first work out the actual proper length. So LV is equal to L naught times the square root of 1 minus v squared over c squared. Now, the fact is that there is a c squared already built in there, so I can rewrite this. So I have 3.57 is equal to L naught, the square root of 1 minus 0.7 squared. Now, if you calculate this out and you rearrange it, your L naught now becomes equal to, and it rounds up to 5 meters. So now I have L naught. Let's do the second half of the question. We now have a new contracted length, our LV, is equal to L naught multiplied by, again, the square root of 1 minus v squared over c squared. And again, what I can do is that I can replace this here just with the ratio of relationship to c, and we're going to call that x. So what I end up having here is that 2.5 is equal to 5 multiplied by the square root of 1 minus x squared. And this is the value I'm interested in. Of course, this is the ratio of the speed of light. So now I get 2.5 over 5 is equal to the square root of 1 minus x squared. If you work this out, x squared ends up being equal to 0.75, and as a result, x ends up being the square root of that, which is 0.866, and so the answer is 0.866C, and that gives me D. Please like, share and subscribe and follow me. Thanks for watching. I'm Paul from High School Physics Explained. Till next time, bye for now.